Hello and welcome. I'm Michael Pierce, and this is The Human Condition. Today we're talking about the EEG and ERP for complementary, alternative, and functional medicine. This is a course about brainwave collection for technicians and for patients to learn about what's going on when we collect brainwaves. So Chapter 5 is EEG basics. We're talking about the basics of EEG measurements and what they're actually measuring, what we're looking for. When we do EEG collection, we are measuring summation, and summation is the idea of really what's called, in my mind, I like to think of it as double summation, meaning that the first thing we're doing is each cell has a summation of all the different signals that it produces. It's got a bunch of arms or tentacles or antennas, and these arms or tentacles or antennas are producing different frequencies of firing. Some of them are fast wave trains and some of them are slow wave trains, and the summation of all of that is the output of that cell. When you then add all those cells together for a certain area, those cells summate as a kind of a cluster or a family or a neighborhood. And then that neighborhood puts out a signal that's perceived by the electrodes on top of your head on your cap as the signal. In today's world, there's a mathematical formula called the fast Fourier transformation or fast Fourier transform. And that was a mathematical integral calculus formula that essentially tears apart the signal and figures out what all the squiggly lines are made of. And so among those squiggly lines that are very disorganized visually, there are alpha waves and delta waves and theta waves. They're waves where the cells as an aggregate are summating to produce a bunch of slow delta waves. And there are also within that some moderately faster alpha waves. And then within that are also some even faster beta waves. When this happens, the mathematics has to be able to tear apart the resulting wave that's picked up by a single electrode. And that process is what allows us to figure out what individual frequencies are buried within a signal. So that's the FFT if you hear about FFT. Then, once we have all these signals, we can then compare them to something called a z-score. And a z-score is where we compare all those waves from thousands of normal people or several hundred normal people, or even people with a particular known problem, to you, the individual, the patient, or the subject, and see how far from typical your resting brain is. Now, once again, to review, EEG is usually resting, but ERP, event-related potentials, is active. You're actually doing something. In most cases for our work, it's going to be something called the P300. And that just means positive 300 milliseconds. So it means there's a positive deflection of the wave, which is usually downward on our convention of our charts, but it doesn't have to be. And that occurs after a person has a stimulus, and the stimulus is usually what we call the oddball paradigm. So the subject is sitting there listening to headphones, and they're hearing a sound like beep, 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 and then at some point they hear a sound they're supposed to be keyed into and pay attention to, which is the oddball sound, and it's usually a higher frequency like beep, and so they hear beep, 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 and when they hear the high beep, they're supposed to click a mouse or click a keyboard key and somehow click a button and signal that they heard it. And so normally every time they hear something, there's a negative deflection at 100 milliseconds, which notes that they heard it. And they didn't do anything, they didn't physically do anything, but their brain registers that they heard it at the top of their head. They register, yep, I heard that, but I didn't do anything about it. So every signal will generate an N100. And then at 300, when there's an oddball sound made, the person kind of says, ooh, I heard something different, and I recognize it, and I'm going to send a motor signal that says, I heard something different, I heard the oddball sound. And so during the oddball sound, there should be the negative 100 deflection and then the negative P300 deflection at 100 milliseconds and 300 milliseconds roughly that says, hey, I heard it, and not only did I hear it, but I noticed it was different, and I'm gonna do something about it. So that's the idea of the ERP, especially the P300. Now there are several kinds of ERPs out there, but the ones that you'll see most of the time are going to be the P300 oddball paradigm. Most of the time it'll be auditory where you're listening for something. Sometimes it'll be visual where you're looking at different arrows pointed at a different direction and you're trying to match up the arrows and decide which of these fits and which doesn't fit. And then you're taught what the oddball paradigm is for your software. So I guess the first thing that we're talking about with these signals is the frequency. And the frequency, as I said before, is how fast does the signal go? And the frequency can be thought of as pitch. So think of frequency like the ability to do work. Or think of it as singers. If we have a chorus of brain cells, the low-pitched singers, the bass singers, are the ones that sing in a very low voice, and they have low frequency, long wavelengths. And so those are called slow waves. And then the middle waves, like the alto and the tenor waves that are not quite as high or low, are intermediate waves, and those ones are a little bit faster, but not too fast. And then the highest pitch or the highest sound, like the sopranos with the high voices, those might be the high beta or the gamma brain waves. And so there's this full spectrum of voices that are singing in this brain as the brain makes its noise. So the frequency shows us what's going on, and very generally, the low frequencies do work that's related to healing and repair and regeneration and sleep, and the higher frequencies do the heavy lifting of thinking. And then the middle frequencies kind of let us idle, they let us relax, they let us be creative, they let us give our brain a rest, but they let us also make sure our brain has perfusion and has blood flow. And so each general area, low, middle, and high frequency, does different kinds of work in different parts of the brain. And the region of the brain matters. I mean, alpha waves in the frontal lobe are different than alpha waves in the back of the brain, and in the right and left temporal lobes. And we certainly don't like to see a lot of asymmetries where there's differences between, say, alpha or theta waves in the left versus the right hemisphere. We generally like to see the brain be symmetric. We don't like to see asymmetric firings. So the next step is the amplitude. And amplitude can be thought of as volume or power. So again, if we go back to the chorus analogy here, like a group of singers, the singers that are singing can sing loud or they can sing soft. And if they sing loud, they have high volume, high amplitude. The waves are tall, not short, because they represent a lot of oomph or a lot of push. We can think of that as voltage, we can think of that as decibels. There's all kinds of ways to measure power, but generally it's power, not frequency. So low frequency doesn't mean low power. Low frequency means, again, like a low voice, like a bass. And high frequency means a high voice, like a soprano. And so high frequency doesn't necessarily mean high amplitude. So a high frequency, low amplitude would be like a soprano singing very quietly. And a high amplitude, low frequency would be a loud bass voice, a basso profundo, just belting out a low-voiced opera type of sound. And so that's how you can get this different symphony of choral music coming out of the brain. So that's amplitude. Now, coherence is another concept, and coherence has to do with how entrained are different areas with each other. So in this way, I like to think of the brain cells all over your brain as a marching band. And if a marching band is marching together, usually they're in step pretty well. Sometimes you hear a marching band that's in step, and you watch them and you see them march, and everyone's marching exactly the same. Their arms and legs are moving, and then maybe they all do a head turn, and then they all do a head turn back. That perfection of synchrony is very high coherence, very high cohesion. And so they're all in sync, they're all in step. And so if you could imagine them as a wave, every single wave would match the other wave. I've often described this to my patients as dolphins swimming in the ocean. If dolphins are swimming together like this, they're in phase with each other. But if you've ever seen dolphins swimming out of phase, they're not quite jumping at the same rate. Now, they may be coherent because they're together, but they're not exactly in phase. They're not in lockstep like that marching band. So think of military marches or marching bands being in lockstep as in phase. Phase has to do with being matched completely, so you're mirror imaging each other, and you're really doing the exact, I shouldn't say mirror imaging, you're a duplicate of the other, you're exactly the same. So if you're absolutely in phase with somebody, you're doing exactly the same thing they do, and if you're 180 degrees out of phase with them, you're doing the exact opposite thing that they do, almost like you would cancel them out. So if they look left, you look right. So this idea of cancellation is where this comes from in phase. So phase is the lockstep matching of a waveform and a brainwave, and coherence is kind of being generally the same. Now, I realize I'm not using math to explain this, so I'll get to the coherence in a bit. Think about the brain cells and realize that if all the brain cells have jobs, and their job is to process information, then we don't want every brain cell doing the same work. We don't want them all processing the same signal. Because if they do, then it's way too much redundancy and it's not efficient and the brain can't do very much work. It's supposed to do some kind of processing over here and then send a signal to another area, and then more processing is done, and then more processing and more processing. And that's done in these pathways throughout the brain, where the brain does its work and then a region does its work and then sends a signal to another region for some more work to be done, and likewise. So you can see that we don't want the brain to be too in sync with other cells, because then everybody's doing the same work and you're not getting much work out of the entire team. It's like everybody doing the same thing. Now, on the other hand, if they're not in phase at all and they don't have any kind of coherence with each other, if they're not in step with each other, then they don't have the same goal, and so they can't finish the work. So you want some bit of coherence with different parts of the brain, but you want limits. You don't want too much, you don't want too little. So you're looking at this Goldilocks range between too much coherence and too little coherence, too much phase lock and too little phase lock. So we're looking at coherence being how similar are the movements of the brain waves, and phase being how exact are the brain waves. We have this mathematics that we can use to say there's too much coherence, there's too much phase interaction, there's too little coherence, there's too little phase interaction between these regions of the brain. So low coherence, high coherence, low phase, high phase, that's all stuff we can look at. Now, not only is there between regions of the brain too much coherence or too little coherence, which again, another way I like to talk about this is imagine a classroom or a workshop of a bunch of people that are on a floor, maybe in a building. They're all working in their cubes at their desks doing their job, and they're all trying to make the company money and achieve a goal, but their jobs are all different, but they're all aimed toward the same goal. So they're somewhat coherent in their work because they're all in the same job, but they're all having different duties within that task, which is to make the company successful. So they have to be somewhat coherent and they have to talk to each other. So in a classroom or a workshop or a building, they all have to talk to each other a little bit. Too much talking would not be very efficient. Too little talking would not be very efficient. So we want to realize that each of these brain areas have to talk to each other somewhat, but not too much and not too little. That's the Goldilocks idea. If the brain is trying to achieve this coherence, one of the things that it will do is we want to know if there is between two areas of the brain, or two electrodes or two regions, is there too much coherence? And if there is, who's the leader in this dance? If these two are dancing together and they're interacting with each other, whose fault is it? Which one came first? Was it this region that drove this region, or this region that drove this region? So that's called directional coherence. Sometimes you'll hear about directional coherence, and directional coherence would be this idea of which area leads the other area, and that can be determined these days with new software. We also might see multivariate coherence, which has to do with how does this region interact with this region, and how does that same region interact with this region, and how does that same region interact with this region, and likewise all through the whole brain. So that's a very complicated system, but it's multivariate coherence, which essentially says how are the networks of the room talking to each other. And that's a thing that we study, along with what I mentioned earlier, which is asymmetry. How much asymmetry is there front to back, side to side of the brain, and these regions working together and having reasonable coherence, reasonable phase, and reasonable amplitudes. We don't want to see certainly high amplitudes or different frequencies in the same region that are across from each other, that are considered homologous regions. We don't want the right side of the temporal lobe over here to be different than the left side of the temporal lobe over here. We want them to be doing roughly the same thing generally. We don't want to see a big difference in frequency, amplitude, coherence, phase. We don't want to see those types of things. The last piece about this is when we're collecting all this data, there will be patients who are interested in what's going on. And if you're a patient and you're asking your technician, and if you're a technician answering the question, it's really important that the technician can't really comment on what these things mean. They can say what we're measuring, but we can't say what it means right now. Let the doctor explain that to you later. So if you're a patient, please don't bother the technician and ask them to do that. And if you're a technician, please don't try to interpret for the patient what it means. Just say we're measuring coherence and amplitude and asymmetry, and the doctor will explain everything to you when they get it all in, and they can study it all. I also want to mention one of the basics of EEG maps is something called the s-LORETA map. The s-LORETA is low resolution tomography, and they call it low resolution, but it isn't really low resolution. It's quite high resolution with good spatial and temporal resolution, but it's called low because when you compare it to fMRI, functional MRI, it's not as good in certain ways. But it is still quite nice in that the resolution of the s-LORETA that I use is about 5 millimeters to 5 millimeters to 5 millimeter cubes. And there's about 6,200 of those cubes inside your brain that we can measure. Not the whole brain, because we can't get the bottom of the brain where the brainstem is and the cerebellum, but the cerebrum, where the lobes of the brain are, you know them as the frontal and the temporal and the occipital lobes, etc. Those areas represent about 6,200 little cubes that are about 5 by 5 by 5 millimeters. And so that's quite good resolution. It's even smaller than a bit of real estate we in the brain we call the Brodmann area. And that's an area of real estate that we mark based on function. And that was done in the early 1900s by Corbinian Brodmann, who mapped out these regions of the area and numbered them up into the 50s about each little area of the brain and what they performed. Some of them perform very psychological tasks, and some of them perform more motor tasks. Some of them perform more sensory tasks. So there's a lot of different tasks that all these 50 plus Brodmann areas do, and they're on either side of the brain. So the s-LORETA is this measurement of deeper areas in the brain. So I need to kind of back up and explain that when the first brain waves were measured, they were measuring electrodes on the surface of the brain. And then after this fast Fourier transformation or fast Fourier transform emerged in mathematics and computers became fast enough to calculate it in real time, they began to map tear apart the waveforms and understand how much alpha, how much beta, and how much delta was in a wave. And they could quantify that and make a QEEG. But at that point, it was still only about 6 millimeters into the surface of the brain. So they were still only mapping surface maps of the brain. So later on came this volume conduction formula where they began to do this, what was called a reverse solution, where they used, again, a bunch of math to calculate what was the likelihood that a signal came from 3 inches deep in the brain. And when it was emerged, when it emanated from 3 inches deep in the brain, it would come out in different directions and it would hit different electrodes. And as that signal hit different electrodes, those electrodes would make a signal. So now the mathematics has to calculate backwards and figure out what was the most likely solution for where that signal came from. And so it calculates all the different possibilities and comes up with the best, most reasonable solution. And that's pretty accurate. And it gives us this picture of where the signal came from. And so that allows us to see not just the surface of the brain QEEG, but a deep QEEG called an s-LORETA. And that's a beautiful picture of deep functions in the brain in areas that are down a couple of inches below the surface. And those are the limbic system. So the limbic system is the system in the brain that is, if you were to break the hemispheres apart, you would see the limbic system deep down on either side, and there's representative pieces of each of the lobes. So there's a chunk of the lower frontal lobe, a chunk of the lower parietal and temporal and occipital lobe that makes up the emotional part of the brain called the limbic system. So the limbic system, it is the emotional part of your brain. It also regulates the immune system. It regulates the endocrine system, the hormone system. It has to do with truth and falsity. It has to do with your beliefs, and there are a great number of studies on that. And so when we measure a person's brainwaves, we're able now, if we have the right software and hardware and a full cap, to get a picture of the person's surface brain as well as their deep brain down to the cortex level of the limbic system. Now we can't yet go down into the thalamus and the basal ganglia. We cannot yet see the hippocampus fully. We can see the parahippocampus, but we can't fully see all these structures. We can't fully see the amygdala. We can't see the brainstem, and we can't see the cerebellum with EEG. But we can see quite a lot, and in combination with a good neurological examination, we can triangulate all the different parts and understand all the different pieces that EEG cannot see. So that's the s-LORETA, which is the deep imaging of the brain and the ability to calculate solutions that help us figure out what signals came from way, way down deep in the brain and ended up tripping our signal receivers on the surface of our brain with the cap. Because remember, the cap is only a surface detector. It doesn't have probes deep down into your head, so it has to report only what it picks up on the surface. So that is the EEG basics, and that's the general idea. One last bit is you may want to know how the maps of the brain are created, there's something called the Talorac Projection, and there's other forms of this, but there's generally a map of people's brains physically that helps us figure out, if you go down this far and over this far, what area does that represent in most people's brains. And so that helps us find where these Brodmann areas are, because we map person's electrical signals on top of a model of the brain that's close to true and within millimeters, which is perfectly enough for our work. Very, very accurate, spatially and temporally, which means in time and space. So this Talorac projection means that when you see a picture of your brain on an EEG or a s-LORETA report, you're going to see this gray-looking brain like an MRI or a CAT scan. That's not your actual brain anatomy. So realize that it's your brain's electrical activity superimposed on a sample brain. And so don't look at that as, oh, I don't have any problems or anatomical problems, because while an EEG can sometimes pick up anatomical problems and even tumors and scars and bleeds, it's subtle, and it's not going to show anatomy the way an MRI would, a standard MRI that you would see with either contrast or no contrast. So I just wanted to mention that, make sure that people understand that we are mapping onto a model of the brain in space when we do EEGs in depth, and we understand where signals came from in your brain from this 3D projection called s-LORETA. And that's chapter 5.